ทำใจก่อนที่มันจะเริ่ม record จริงๆแป๊บนึงโอเคเร็วแล้วนี้ alright so now that we've taken the break let's resume the class and talk about what is a computer right so let's talk quickly about what is a computer because that motivate every single thing we do in this class and it's actually become the foundation of every single thing you do in computer science and computer engineering. Everything exists because there's a computer, right? So if you go to Oxford English Dictionary, that would be like the first thing we can do, right? As a PhD, you need to have this skill, right? If I don't know how to define a computer, I'll go with some of the source I can trust. I'll go to the dictionary, right? And see what do they define? That would be like a really naive solution where I'm not going to use it. But let's see, right? An electronic device for storing and processing data, typically in binary form, according to the instructions given to it in a variable program. And that's a pretty darn good definition of a computer. Why is that the case? It's an electronic device. That's the computer that store and process the data, right? It store and process the data, typically in the binary form, right? According to the instruction given, the whatever we program in it, in the variable program. That is a really good, concise definition of a computer. This one definition make it such that a calculator, which is not a computer, it distinct what is the difference between the calculator and a computer. You cannot program and store the program in a calculator unless you talk about TI-89 and better, right? Those are fancy calculator that actually have computer chips in it, right? So those are computer already. But at the end of the day, right, it's a device that can store your program, run your program. They're done electronically in a binary form based on whatever you program, right? So let's look deeper, right? So logically, it's a bunch of logic gates that compute whatever you want to do. A plus B, C multiplied by D, X minus Y, A and B, right? These are what the logic gates are for, right? To do the logical operation. Add and multiply and everything can be built from logical operation as well. If you don't know that, now you know. You can build an adder from an and, or, and not. And, or, and not. You can build those and make it an adder. Control signal to communicate, to make sure one component can communicate with the other. I'm doing an add, where's A, where's B, take those as an input. Okay, I'm adding them together. Those are the communication elements of your logic. You need to be able to coordinate everything. And then there's a storage element, right? And physically, they are all just transistor, capacitor, wires, and resistor. We are not going to go any more than this, right? We're not going to go any more on this, but just have this image that every single thing we do are physical devices like transistor, capacitor, they exist, right? And logically, it's just a bunch of math functions, right? It's just a bunch of bits that somehow mean something. So if you kind of want to look at it in a different angle, right? You have the processor, you have the memory, and you have I/O. And that's kind of all, actually. The processor is like your CPU. The memory is basically whatever memory, like DRAM, like you go to computer store and you buy DRAM, that's your main interface between the I/O and the processor, right? If you will, I would like to use this word. I'm gonna change to Thai, right? ให้คิดว่า memory เนี่ยมันเหมือนกระดาษทดที่แบบเวลาผมมีโปรแกรมใหญ่ๆแล้วผมจำไม่ได้หมดอ่ะ คือมันจะดูดโปรแกรมนั้นแปะไว้ในกระดาษทดแล้ว processor คือสมองผมก็จะ operate on กระดาษทดอันนั้น Alright, now switch back to English. So yeah, memory works like a scratch pad, right? Where you can store temporary data, you can store the program and it interface with your processor or your brain, if you think about the processor as the brain of the computer. And when did we have this concept of a computer, right? It actually has been around for a long time. Anyone heard about the mechanical calculator? So these are calculator basically that works not digitally, but through like mechanical parts, right? Or the Jacob's loom. So loom in Thai is เครื่องทอผ้า อันนี้ก็คือเครื่องทอผ้าของคนที่ชื่อ Jacobs นะครับ มันเป็นเครื่องทอผ้าชนิดหนึ่งเดี๋ยวเอารูปให้ดู Alright, so the Jacobs loom is actually pretty interesting. This is an image of the Jacobs loom, right? So you can see that there's a bunch of punch hole here. That's the pattern that you want. And think of it as a program because you already punched different hole, right? And you can use these pattern. You can pick which one you want to use, put that on the machine as if you install the program, and then the machine or the loom would put all the threads together, into a piece of cloth, right? So now actually you might have noticed a lot of things a lot of words that we've been using in computer science. Thread, right? The thread is a unit of uh, uh, work management system. The way I would define it is like it's a group of work that the program assigned for the computer to do, right? And that's currently being managed right now by the system. That's called a thread, right? This tool here, that bundle all the threads together is actually called a warp. NVIDIA actually used this exact word to call a bundle of threads that runs on the GPU, right? So this is basically more like a historical reason, right? It's a loom that can be programmed. ขอแปลไทยนิดนึงนะครับมันก็คือเครื่องทอผ้าที่แบบเราเขียนโค้ดได้ไอ้โค้ดทางขวาเนี่ยไอ้ที่เป็นเจาะเนี่ยมันเป็นรูที่ให้เส้นได้มันวิ่งเข้ามาแล้วเครื่องเนี้ยเราสามารถหยิบได้เราจะเอาแพทเทิร์นไหนแล้วก็สดใส่เข้าไปในเครื่องแล้วไอ้เครื่องทอผ้าเนี้ยมันก็จะทอแพทเทิร์นที่เราโปรแกรมไว้ก่อนได้แมจิกไหมแมจิกSo we've been thinking about programming stuff for a long time, right? So that's kind of like what we use in the textbook in the class lecture as like the dawn of digital computing, right? But the actual like true first digital computer is called ENIAC. Anyone heard about this machine, ENIAC? เคยได้ยินกันไหมครับ ENIAC?
ใช่ครับ
All right. So if you happen to be able to visit the University of Pennsylvania, the university in Philadelphia, Pennsylvania in the US, they have a museum with an actual ENIAC machine. So this is a picture I've taken. Sorry about everything looks yellow. There's like my camera is like potatoes at the time. It's like 2000, I think 2005. This picture was taken 17 years ago. So this is an actual machine. That's the ENIAC, the first ever digital computer. It can be programmed. It's at the University of Pennsylvania right now. It has 18,000 vacuum tubes. It weighs 30 tons. It's a huge machine. Look at the thing itself, right? And I guess you get the reflection of, I think, my friends right here, and I think there's a bunch of us like basically right there, like on the mirror. Is compute 20 decimal digit words, basically 20 decimal numbers, program using all these switches, right? That you can see in the picture, right? So this is a machine, I think in 1950 something, right? But before that, you might have seen some instance of it. How many people have watched the imitation game? มีใครเคยดูหนัง imitation game อะครับที่ Benedict Cumberbatch เล่นเป็นพระเอกที่เป็น Alan Turing ฮะมีคนตามทราบดูมีคนเคยดูแนะนำให้ยังไม่ดูสนุกมาก so you might have seen those machines too, right? Those are called the Bombay. And if this machine is in 1950, when is World War II? When exactly is World War II? Oh, around what years? All right, history reason. No, sorry, history lesson. So it's between around. I actually forgot the start date, but I think it's 1939 to 1945, right? Is 1945 before 1950? The answer is yes. But aren't those computer? So what is the difference? Why do we call ENIAC the first digital computer and we don't call the Bombay the first digital computer? Any key difference that you see from the movie compared to this thing?
มี
น้องๆ
transistor
ที่
ป่ะครับ
อะไรนะครับ
มี transistor ป่ะครับ
มี transistor หรือเปล่า จริงๆ ก็เกือบใช่ อันนี้มันเป็น vacuum tube มันไม่ใช่ transistor มันจะเล็กกว่านี้ แต่ว่าวิใครดูหนังจำได้ใช่ป่ะ เวลาโปรแกรมอะไรมันหมุนมันมีแบบจานหมุนอยู่บนเครื่องอะจำได้ไหมครับ
Because it's only solve one problem, not multiple problems.
So you can actually program that thing, but the thing is, it's more mechanical, right? You use the gear and everything to help solving the program, right? So that's the key difference. That's why we add the word digital computer, because this thing is actually all electric, to be honest, right? If you will, basically, it's all electric. But I mean, if you think about it, if you just break the image about what is the first, right? If you look at the 1940s, there's a lot of hardware advances. The war effort actually is to be honest, I think it's probably play a major role in that as well, because information warfare is important. You need to control information, otherwise you can't make plans, right? So there's Atanasov and Berry called the ABC. There's like C3, C4, the SUSI. These are from the German side, the C3 and C4. I think one of them actually got bombed. There's a Colossus by Turing and the Bombay. The Bombay is the one that you saw on the movie, and then they built the Colossus afterward, if I remember correctly. I think that the order is Bombay and then Colossus. That's from the British side. That's ENIAC, right? That you saw. That's from the US, from Eckert and Moschly. By the way, the two names, Eckert and Moschly, becomes like the name for like one of the top award in like people who contribute a lot to more of the hardware part of the computer science. The EDVAC, right? EDVAC is built by von Neumann. Anyone heard about this name, von Neumann? So von Neumann, by the way, is also the name of a really top award in the engineering side of things. So Turing Award is from the computer science side. That's also von Neumann Award. So he built the EDVAC, and that's when the way we run the program as we know it these days is being invented. It's called von Neumann Model, and we'll learn about it today, actually, in a bit. There's also EDVAC, built by Wilkes, and Wilkes actually built now the first store program. Now, the first store program means that it actually is capable of actually put the program on a machine and run it, right? And then there's like Bigelow built the IIS, and then after after we have the first store program, it means that now you can write a lot of programs, right? So after the 40 and 50, then you have the emergence of software. The emergence of software. Why is that the case? Back then, hardware is super expensive. Human labor is cheap. We as an engineer, we become the operator of the machine because our salary is a lot cheaper than the cost to build this thing. This thing is so expensive to build, right? So back then, hardware is expensive. They don't have a lot of machine in the world. Computer engineer, our salary is a lot cheaper combined compared to these things. So afterward, then you have a lot of software code because once you put a lot of human together, we build things, right? We build the hardware. Now the hardware is built, so let's build the software. So there's an emergence of software like Fortran in 1954, and then becomes the dawn of computer as you know it, right? And then you run into the age of Moore's law. Now, today has to be a lot of history lesson. So what is Moore's law? Moore's law basically dictates that there'll be a number of increase, right, in transistor every certain number of years. So it doubles every 2 years, and it's been following this trend for a while, for a really, really, really long time, right? And these days change a little bit. I actually forgot like what's the rate these days because it's actually really hard to make a transistor smaller these days. Also, someone was making a joke because Gordon Moore owned Intel, right? Whatever he said, Intel engineer has to do it. So Intel engineer was like, okay, fine, I'll redouble every 2 years. That was a joke, by the way, but I mean, if you look at the observation, it closely resembles Moore's law, right? It's actually just an observation back in 1965, right? Cramming more component onto integrated circuits. So that's a paper itself. So you might be wondering, how many people wonder, why is it so important that I can add more transistor to my CPU? ถามครับแล้วผมเติมทรานซิสเตอร์เข้าไปเยอะๆอย่างเงี้ยมีประโยชน์ละหรือแบบทำให้ทรานซิสเตอร์ขนาดเล็กลงมันช่วยอะไรได้มันจะมีประโยชน์ยังไงให้ลองคิดนะครับไม่อันนี้เป็น open discussion เลย
มันทำให้คำนวณได้เร็วขึ้นป่ะครับ
ผมสามารถใช้ทรานซิสเตอร์จำนวนมากขึ้นเพื่อยัดเข้าไปให้มันก้อนที่คอมเพล็กซ์ขึ้นเพื่อจะคำนวณอาจจะคำนวณ operation fancy ได้หรือผมอาจจะใส่แคชมีใครเคยซื้อ CPU ประกอบเครื่องเองปะครับถ้าสมมุติไม่งั้นก็คือเลือกสเปคแล็ปท็อปอะไรเงี้ยแล้วดูว่า CPU มันเป็นรุ่นไหนสเปคใน CPU มันจะบอกว่า cache L1 cache L2 cache ขนาดเท่าไหร่ให้คิดซะว่าไอ้ cache เนี่ยมันเป็นแบบหน่วยความจำอันเล็กๆแต่เร็วมากๆเร็วกว่าหน่วยความจำไอ้ memory ที่เราใช้เยอะมากๆยิ่งใหญ่เนี่ยมันก็ยิ่งเก็บข้อมูลใน CPU ได้เยอะก็ผมอาจจะเอา transistor มาใส่ cache เพิ่มก็ได้หรือจริงๆแล้วทุกอย่างที่เราจะเรียนกันในคลาสเนี้ยมันต้อง implement ด้วย transistor เพราะฉะนั้นถ้าเราอยากจะทำให้ CPU มันเร็วขึ้นผมก็ต้องใช้ transistor เพิ่ม so basically if you think about it right if you want to make your compute unit faster you need to use more transistor right again everything looks like black magic but it actually does cause a physical component right so these are why more transistor program always want more performance right the transistor we can add is the resource that can be used to address the performance bottleneck and we can do this over and over and over again. That's another reading on the reading list for the first review. This is one of the potential papers you can pick from. It's from Yale Path. The paper is more of the paper that look forward. It's not the technical paper. It talks about requirements, bottleneck, and what are the good problems for the evolution of microprocessor. This was published in 2001. If you're old enough, you might remember around 2001 is when you start to have dual core. So if you look at Intel chip, there'll be Pentium 1, Pentium 2, Pentium 3, Pentium 4. Those are all single core CPU, right? And then Intel basically said, hey, we can't manage the power budget anymore. If you want to make a single CPU faster, will consume too much power. It would heat up your computer and everything goes bad. So let's use multi-core. Multi-core. So you have dual core, quad core. Now you have 6 core and 8 cores machine, right? That was changed around 2001. So the paper looks forward. This is an interesting paper. It's different. It's more like a keynote talk where it looks forward. And look at what are the good problems that researcher, us, PhD students, should look into from the perspective of someone as senior as Yale Pat, right? And when you read the paper, you might notice a lot of things over there is becoming true, right? Becoming the actual invention afterward. So if you look at modern computer, the things like Raspberry Pi, like the GPU, these are the cluster. The picture taken, I think I borrowed the picture from the Lawrence Livermore National Lab from their website, right? These are cluster of computer. You can look at your phone, right? There's also computer. Things that control the GoPro is also a computer. Or this. Anyone notice what this is? Anyone want to take a guess? What kind of computer is that?
quantum computer มั้งครับ
ใช่ครับ so that's a quantum computer. It's a different type of computer as well, right? So modern computer can vary in shape and form and the way you think about the compute model. The quantum computer doesn't even have the proper ISA and compute model yet, right? Because it's still in research. We are still trying to figure out what's the best way to program and to manage the computer, right? And in my opinion, that's a really, really good research direction as well. If you want to look into that, right? How to actually program, like what's the best way to program this thing? And how do we actually build maybe things like programming language for these things, right? It's still something that we haven't really finalized yet. And to be honest, even programming language like Python, Java, C, right? We never finalize it. We just keep making it better, right? And what happened when you run a program? Basically, let's say you have this really simple program. I is 10, J is 20, K is I plus J, right? In the next lecture, I'll go into more detail on what happened. But if you think about it, you have this code, right? This code is basically a program. Then you feed that to the compiler. This is a C code, so you go into the GCC compiler. It basically spits out the assembly, the binary, basically, ones and zero. It's 1 and 0 that somehow the computer understand. Then when you run it, the OS comes in and say, hey, run this. The way they run it is basically they copy the code, put that code on your memory. Then it tells the CPU, hey, the code starts from here. The CPU takes the code and know where is the starting point in the memory and it keep running. That's all. It looks at the ISA and say, okay, I see this pattern. Is that an add? Is that a multiply? Is that a load instruction? And then it basically works its magic on the hardware design and make sure you can produce the output. And that's all. That's all what happened when you run the program, right? So in this class, we'll learn about mostly the microarchitecture, but we'll also learn how the runtime and ISA interact with the microarchitecture and make it run, right? And again, because I want to kind of leave today with like the compute model. You've seen the name von Neumann, right? So the von Neumann model is basically this. It's a store program computer. There's 2 key properties. Programs is in the memory. It's linear. By the word linear, it's basically it's like all the lines in your program sit next to each other. And the memory is unified between your instruction and the data. And the control signal basically try to figure out, is that the data or is that the instruction? And then it performs sequential instruction processing. This is important because you do one instruction at a time. fetch the instruction. Basically, I go and grab the instruction. I look at what the instruction is, execute it, complete. Fetch the next instruction, look at it. What is that? Add, multiply, execute that, complete. Then I look at the third instruction line by line by line by line. To figure out what line am I at, there's a program counter. Program counter basically points to the current line that I'm running. It identifies the current instruction. In some textbooks, sometimes we call this instruction pointer. Sometimes we call this program counter. It's the exact same thing, right? And you move the program counter to move from one line in the program to another. That's basically how you run every single program that are not functional programming. Python run the same way. C code run the same way. Java use the same one Neumann model. Most of the programming language, unless you're looking at functional program, they use one Neumann model. What does it mean? You run the code line by line by line by line by line. The first line, then the second line, then the third line, then the fourth line, then the fifth line. Then the program is in the memory, data is in the memory, and that's it. That's the model. Why this model? It's simple to program. That's how humans think. I think line by line by line by line, right? So I can program easily. And the way one Neumann works, right? You have the input and output, that's the I/O. The blue thing is in your CPU and the green thing is in the memory, right? The input comes in, it copies the program into the memory. The processing unit goes into the memory, read the program, figure out where is the program code, the first line. Then it handle the processing and spits out the output eventually, right? And then the dashed line, these things are control signal, basically control the input, control the memory, and control the output. That's kind of like a really, really, really high level overview of how you run the program. But I'm going to go into more detail soon. And I will also go into more detail of all these components going forward for the future lectures. Now, is this the only model? No, because I said, most programming languages use this model except for functional program. So functional programming will use a different model. But this is one of the most dominant. It's used everywhere. All major ISA that you use nowadays, ARM, MIPS, Spark, Alpha, x86, IBM Power, they use one Neumann model. That's why it's so important, because it's actually simple. It's really simple. So what's the alternative? The alternative is called the Dataflow Model. So one Neumann execute instruction in the control flow order, line by line by line by line, unless you see if else or for loop. Those are control instruction, and you jump from one to another. Instruction pointer grab the next instruction, and mostly sequential until you run into if else or for loop, right? Otherwise, you run the next line. Dataflow model, instruction is fetched in the dataflow order. I look at instruction as a math function. I look at it as a math function. If I have all the inputs ready, I fire off that instruction. And that makes the name Dataflow model, because if I have all the data ready, I will spit out the output, the new data. Right? It computes whenever the operand. Operand, basically think of the word operand as an input to your function. When I have all the inputs, I run the function. There's no instruction pointer needed, because every function would spit out the output and someone else would catch it, right? And run the next function. Ordering is based on dataflow dependence. Think of this as a math function, right? If I have all the inputs, I can execute that math function. I spit out the output. It becomes the input to the next function, and so on and so forth until the program finish. So many instructions can execute at the same time. This is better for parallel programming and parallelism. That's why you might see language like Rust. Anyone use Rust before? So if you have not used it, let me post the link of the site that talks about the last language. It's a really, really nice language if you want to write parallel programming. It's one of the best, actually, if not de facto the best right now. It managed the memory really well and it's really fast. It's really, really fast, right? So that's kind of like follow more of the Dataflow model. It gives you parallelism, right? And then let me tell you the difference. Let's say I have a code that looks like this. C equals A plus B, X equals B multiplied by 10, Y equals B plus X, and C like SAT equals C plus Y, right? So that's a sequential model. So let's assume each instruction take 1 second. How long does it take for me to finish on this thing? If each instruction take 1 second, how many seconds in total would I take to finish this? 4, right? I have 4 lines, 4 instruction, so 4 seconds. Let's look at this in the Dataflow order. I can do the plus and multiply at the same time because there's no dependency here. A and B is the input to the add. B and 10 is the input to the multiply. I have all my inputs, so I can do it right away. I do not have X. I do not have Y, so I cannot do the third and the fourth line. So I first do the first 2 lines together in parallel. Then I have X, so I can do Y equal B plus X, right? I'm still waiting for Y. So the last line, C equals C plus Y. That can be done at the end. But because we do the add and multiply the first step in parallel, from 4 seconds, we reduce that to 3 seconds, right? But the thing is, as a programmer, the left side is a lot more natural. The left side is a lot more natural. The right side is faster. The right side is faster. In this class, in this semester, we will learn how your CPU convert the left side here and run things in the right side here. Magic within your CPU. This is actually being done. It's done on the CPU. It's not done on a GPU. This is done on the CPU only. They convert sequential instruction processing into something that imitates data flow and run things out of order. Try to do it in parallel. We'll learn about that. It's called out of order execution. We'll learn in about 4 or 5 lectures. But there's also, if you look at data flow diagram, there's multiple types of data flow node, like computation, conditional, relational, barrier, and synchronization. Basically, wait for every input to become ready before you move forward together, right? So these are some of the samples, and I would give you one example here, and I'll give this as an extra credit. The next time we meet again, I'm going to ask and explain what is this logic. But for now, if you can give me the explanation of what is this logic in the next lecture, I'll give the extra credit to whoever can give me the answer. All right. So I'll post a PDF of the PDF of this slides on the class website. And my question right now is, what does this data flow program do? Right. And before we go, other things. Lab 1 is actually now available. You don't have to do it now, right? You don't have to do it now for sure, because we haven't really learned ISA. We haven't really learned anything yet, but it's there. Dealing with online lectures, you want to ask as many questions as possible. That's something I want to highlight. Put the question in here. If I'm going too fast, stop me and ask me. You can ask in Thai, you can ask in English. It's also fine. Raising your hand helps me identify that you actually want to ask questions or pause, because as I said, I talk a lot, right? And that's it for today's lecture part. So let me say welcome to ComArch at VISTEC. And for the remainder of the time, so let me stop the recording.